We will now have a presentation by Tom. He's studying here in the University of Edinburgh, and that's your turn now. Well, a few minutes late.
Okay. Good afternoon, everyone. As my friend here says, my name is Tom Spink. I'm a PhD student here at the University of Edinburgh. So I realise you've been here for a day and a half already, but I still would like to, on behalf of the Informatics Department, welcome you here to Edinburgh. I'm going to be talking about custom alias analysis in an LLVM-backed, region-based dynamic binary translator, and this is in the context of an instruction set simulator. So the way I'm going to structure this talk is to just give a quick overview of dynamic binary translators for those of you not familiar with the subject, and also specifically instruction set simulators. Then I'll talk a bit about our instruction set simulator that we've developed in our department, what components go up to make it. And then a bit about the LLVM bitcode generator that we've got inside there. I'll talk about the problem that I've encountered and the problem that I had with alias analysis in LLVM, what our solution to that problem was, and a challenge. It says challenges, but it's actually just one major challenge was getting the alias analysis in. Then I compare us to QEMU and just give a couple of other teasers about our instruction set simulator. So dynamic binary translators in general will take machine code from one instruction set architecture, one ISA, and possibly translate it to a different ISA, or it may be the same ISA. So Intel's PIN is an x86 to x86 dynamic binary translator, but the likes of QEMU will maybe take ARM and convert it to x86. So we might even instrument the code as we're doing it. So that's what you can do with PIN. You can instrument your code. We may even optimize the IR. Typically, we'll take some input machine code and convert it to some IR. We might optimize this IR and then output some new machine code in whatever our host instruction set is. And an instruction set simulator is designed to emulate some target ISA on a host ISA. We can build it as a simple loop and switch interpreter, so we just fetch an instruction from the input binary, loop around, execute it, and then do it again. So we fetch the next instruction, execute it, and keep going around. We can do better than that. We can do threaded interpreters there. So as you can see, we've got this not working laser pointer. A simple threaded interpreter where we take these different and we directly branch to the implementations of the instructions. We can build a static binary translator, which typically will just take the input binary that's in one ISA and statically compile it to the target ISA. And also we can be much more clever and we can build a dynamic, an instruction set simulator on top of a dynamic binary translator. And here's an example of a dynamic binary translator instruction set simulator. This is the way that QEMU works. It'll start executing a target basic block. So this is a basic block of instructions in the target ISA. It'll look at that block, it'll fetch that block of instructions, it'll translate that entire block, and then it'll execute that entire block. And typically it'll cache the block as well, so that when we come back around to it, when we encounter that block again, we can just take that straight from the cache and execute that directly. So that's how QEMU works. And our ISS this is what I'd like to talk about now. We've got two major components that belong to our ISS. We've got GenSim and ArcSim. Oh, thank you. And the GenSim component is an offline processor module generator, so about that in a second. And ArcSim is the actual instruction set simulation framework, which consumes what we've generated in our GenSim offline stage. So GenSim, it takes a processor description and it takes instruction behaviors written in a high-level language, it combines them together, and it generates a processor module. Right? So this processor's description is written in a variant of ArchC, and the instruction behaviors are written in a C-like language. So it's a high-level description of the implementations of the instructions in our instruction set architecture. And our processor description includes information about the processor that we're emulating. So it'll contain the registers that are available, it'll contain the flags and things like that. And then it'll also contain the decoding information of the instruction set architecture, so how we actually decode the instructions, how we actually turn the raw instruction stream into the decoded instruction, and then which will be executed by the semantic description in the instruction behaviors. And GenSim takes all of this together. What it produces is this processor module which contains an interpreter, and it also contains an LLVM bitcode generator. So the interpreter is just a simple loop and switch interpreter. I'll speak in detail about the bitcode generator in a little while. So ArcSim, which is the online part of this, which is the actual instruction set simulator, what this does is this takes the processor module that we have generated in our offline stage. So given our processor, say we've got a working model for ARM v5T. So once we run that model through GenSim, we've got our processor module and our interpreter and our bitcode. We use this module, ArcSim uses this module, and it also takes in the target binary. So this is the binary compiled in the instruction set that you want it to emulate, and it runs it. And initially what happens is the code from the target binary is interpreted, and as we interpret it, we also profile it into regions. Okay, so these regions that we talk about are they're basically 8K blocks of code. So it's a couple of pages if we. Of code in the target binary. So we split up the binary into these 8K regions, we interpret the code, and we map the entry points to the basic blocks in these regions. So a region can become hot, and this is after it's exceeded some kind of execution threshold. And when these regions become hot, we then know that they're eligible for compilation, and we send them off to an asynchronous worker. And this asynchronous worker deals with all the compilation of the region, but as it's doing that, we're also still interpreting at the same time. So we're continuously executing code, we're interpreting, we're compiling in the background, and as we're doing that, as the program's executing, the compilation threads, what these are doing is these are taking these regions that we've generated. So we've got these basic blocks in here, that we've discovered in the target binary. This one down here that's grayed out, that's actually a block that exists but hasn't been discovered yet. Also, the grey arrows there, that's control flow information that hasn't been discovered yet but may exist in the future. These regions that we know about, and the basic blocks within the regions that we know about, they are essentially what we do is we create one single LLVM function to represent this entire code region. And within this LLVM function, we create one LLVM basic block for each target basic block that we've discovered so far. The situation is a bit more complex when we start generating code, but essentially this is how we start off. We start off with one LLVM function, we start off with one LLVM basic block in the function for each basic block in the region, and we take it from there. So inside the target basic block, this is the ARM example that I've just been talking about here. Inside that basic block, we've got some ARM code, and we consider each instruction that's inside that basic block. Okay, so when we iterate over the instructions in the basic blocks inside the region, what we do is we just fire out LLVM IR for that instruction. So we encounter each basic block, and for each basic block we encounter each instruction in the basic block, and when we come to add, we just fire out the IR that corresponds to an add instruction, compare, store, add, and then our branch, we do some chaining code to get to the different basic blocks there. And so we end up with a lot of basic blocks in the region, and a lot of IR within those basic blocks. And once we've got our function ready, once we've got all the basic blocks, we may have introduced some more basic blocks to account for dynamic control flow that's within an instruction description. And also for the likes of ARM, we have predicated instructions, so we also will need to introduce additional basic blocks to account for control flow around predicated instructions. Once we've got all that, we link it quickly with some architecture-specific bit code, and that's generally just how to read the PC register, and in the case of ARM, again, it contains the predicate logic, and that's generated in the offline stage. We generate that from the processor description. So we link it all together, we run some optimizations across it, which are based on the O3 optimizations, taken straight out of the LLVM source, and we compile it with the venerable get pointer to function instruction. So what we end up with is a pointer to this function that we've generated, which contains native code now for this region of code that we've discovered during profiling. And then finally, the execution engine, once this function is registered, the execution engine, after it's finished interpreting the last block, it'll come around, it'll discover that we have a native translation available for the code, and it'll jump straight into it. And we can actually, if we then get to control flow that we haven't seen, we'll come back out into the interpreter to interpret the code, but then we'll build up this information, and the region will become eligible for recompilation, so we'll recompile it again in exactly the same fashion, but with the extra information that we've now discovered, and given that we would get a much more efficient function with much more native code. And typically, once we've warmed up and everything is going, at the end of the run, we'll end up executing about 98%. We'll be actually executing native code and not interpreting. The rest 2% is just interpreting. So that's a quick overview of how the system actually works on a high level. I don't want to go into too much detail because that's not what this talk's about, and I promise I will get onto alias analysis in just a second. But a bit about the bitcode generator here, because this is fundamental in understanding why we've had the problem with alias analysis. I've already mentioned here we make the target basic blocks. So I think, we iterate over each instruction, and the only thing to note on this slide actually is that we employ this partial evaluation technique. So instructions can have different behaviors depending on what flags are set in the instruction. So if I go back to our like ARM example, we have an add instruction which may be add S, or it may be add on its own. So the S flag says that we should set flags after this add. That's something that's we can determine at static JIT compilation time, and we only emit the code that corresponds to setting the flags if that bit is actually set in the instruction description. So we don't bother emitting any IR that's not relevant to the instruction that we're compiling. So that saves on a lot of IR. There's no point emitting IR that's never ever going to be executed. LLVM would probably optimize it away, but why bother giving LLVM more work to deal with when we can just statically not emit that IR and reduce the IR code size considerably. So now I will talk about the problem, and this is the problem here. So we notice a severe, well, firstly, we notice a severe performance deficit in comparison to QEMU. So that's a problem because we want to be better than QEMU. We want to be much better. And ultimately, one of the problems was that we tracked it down to redundant loads and dead stores still existing after we'd ran the alias, after we'd ran all of the standard optimizations. And so here's an example of some IR here that existed after our optimization. So we've got the store up at the top here, then we've got a load and an add and a store back to memory. And you can see these stores here and this load here, it's actually operating on a constant pointer. And this is one of the optimizations that makes our ISS really fast, is we support something called contiguous memory, which means that we can generate code that directly accesses a region of memory that represents the guest memory area of the binary being executed. And because of these constant pointer accesses, things like these stores here, the existing alias analysis implementations, they're unable to determine whether or not that actually aliases with this constant pointer here. And what we can see is that this here obviously is completely redundant to that. And then this one here actually completely kills both these two stores here. And it's a problem because once we lower this IR, this is what we get. This is some x86 machine code. We get exactly what you see. We get a MOV straight into memory there, a MOV straight into memory there, and both those MOVs are killed by this MOV here, okay? And this is the problem. And it's not because the alias analysis is bad. It's just because they just haven't got enough context to work with. Because fundamentally, what we're doing is we're just compiling snippets of a program. We're not compiling a whole program here, so we don't have information about everything. We're compiling just these IR fragments that have been pasted together and generated. And it's not because they're bad, it's just they just don't have enough information to work with. They don't have enough context to make reasonable decisions about whether or not pointers alias. And if we made the alias analysis passes more complex, we'd introduce unnecessary delay. And that's not good in an instruction set simulator that's trying to be fast. We don't want any delay. And it turns out that actually alias analysis itself, what it's doing is it's trying to recover this aliasing information for feeding into the dead store elimination and redundant load elimination passes. But what's the point in trying to recover this information using logic when actually we have this information at generation time? We know exactly the IR that we're going to generate, and we know exactly what the IR that we're generating does. We know what the int pointers point to. We know what they point to guest memory. We know that the get element pointers point to virtual registers in the CPU state struct. And what's the point in trying to recover this at runtime with a complex analysis pass when actually we can propagate that information down at generation time? So this is exactly what we do. LLVM doesn't distinguish between our simulated memory operations and our virtual register operations. Here's an example of a guest register write. So this, from the top of my head, it looks like it's loading some value and then it's storing it into virtual register R3, okay? And this is a guest memory write. We're actually loading a virtual register here, R1. We're doing some magic here to calculate the address where that lies in our contiguous memory space. We're getting that back into a pointer, and then we're storing the value that we've loaded from the register straight into memory. And the problem is that, well, I've told you what the problem is, and this is the solution. This is decorating our get element pointers and our int pointers with custom metadata. So this is totally cool, and I love LLVM for this. Is the fact that we can add this information at generation time to our instructions that we're generating. So we introduced this metadata node here called AAAI, which is ArcSim Alias Analysis Information. And what we do is we insert a custom alias analysis pass that consumes this custom metadata and reasons about the aliasing of pointers directly from the metadata. So encoded in the metadata is the actual aliasing information that we use in the pass. So the alias analysis pass isn't actually an analysis at all. It directly, there's no analysis that happens. It directly uses the information from the instructions metadata to say whether or not a pointer does alias, whether or not it doesn't alias, and perhaps if it really can't work it out, then it may alias, which is of course the conservative answer to the question. So we insert this metadata at generation time because we know what our gep does here, we know what our gep does there, we know what our interpointer's for down here at the bottom, and then our alias analysis pass that we make uses this metadata of this propagated aliasing information and answers the queries that the different optimizations that will use very, very accurately. And what we do in our metadata is, I've said that we encode this information in the metadata and we introduce different aliasing classes. So we introduce an aliasing class for CPU, state and flag accesses. Those are actually two separate classes. We introduce a class for virtual register access, guest memory access, and we also have some internal JIT state structures which makes us even faster because we do clever things like region chaining and whatnot. And these are all accesses to memory which we need to provide aliasing information about. And what we know is that no operations on pointers that exist in two different classes can possibly alias. We know that. That is fundamental here. Okay. So if you take a look at this get element pointer here that accesses part of our CPU state structure, we've decorated it with metadata 14 here, which has alias class 5, which is part of our region chaining table. And then the get element pointers here, that's metadata 18 and 19. Those are both virtual register accesses. So the first operand in these nodes down here is actually determines the class. So 5 represents this region chaining, 2 represents an access to guest memory, 1 down here, these are all virtual register accesses. And then what we also do is we further specialize these metadata nodes with information about specific to the type of operation that's happening. We have no more information about a guest memory access, so we leave that as it is. A region chaining table access doesn't require any more information. But virtual register accesses are quite interesting because we can access different virtual registers. We have banked virtual register accesses. We have flag accesses. And so what we do is we have our type of access here, and then this next element here, this next operand tells us what bank the register is in, and then this last one tells us what the actual register index is. So we can actually use this to determine whether or not some pointers are going to alias. Some pointers are going to alias without actually analyzing the instruction that's being asked about by the alias analysis infrastructure. We can actually just use the metadata and say yes or no without having to scan through the get element pointer instruction and work out whether or not the operands match up. So here's a quick example of two classes that definitely do not alias. There's our two instructions. So our alias analysis pass has been queried for this information of these two elements, these two instructions here. One has metadata 15, one has metadata 18. First operand here, operand 0, they're different classes. So we instantly say no alias. We know that, okay? They definitely don't alias. And so for the register example here, we've got these two register accesses. So these are getting the element pointers to the virtual registers in our CPU state structure. Metadata 18, metadata 19. Same class here, so we need to be a bit more clever. Same register bank, but different register indices. Okay, so in our if statement, we're checking the first bank. The bank is equal. Okay, so now let's check the register index. If the bank was not equal, obviously they don't alias. Different banks, no aliasing going on here. Then we check the register index. Is the register index the same? Well, if the register index is the same, they obviously have to alias. Okay, because it's the same register, right? And if the register index is different, then they can't possibly alias. So we can give definite answers to these by just using the information that we've encoded directly into the metadata here. And the challenge that I came across is that inserting a new alias analysis pass is actually hard, and it's because you can't change the default. This is as far as when I developed this was how it was. You can't change the default alias analysis implementation. So what I did was I created this inline helper method, add pass, which whether or not you set this boolean to true here, this with AA flag, it would add an ArcSim alias analysis pass before the actual pass that you wanted to add in. So down here is the code that actually builds the pass. So we don't use a pass manager builder because we're actually building the pass. We're putting each pass in the order. But this is actually based on the source code of the pass manager builder because we're just taking standard O3 passes here. We need to initialize the alias analysis infrastructure. So we add this type-based alias analysis pass at the very start before we do everything. That turns everything on, and then we add a pass to the pass manager. we had all the standard passes, and this with AA flag, it's a command line option basically, so you can turn on alias analysis or turn it off. You can turn on or off our custom alias analysis to see what the sort of effects are between things. And if alias analysis is turned on, then before each pass we'll add the ArcSim alias analysis pass every time. Obviously not every pass requires that information, but it's safer to just stick it in there just in case the requirements change in the future. So that's actually the only major challenge that we had, other than when I ported the system over from the old JIT to MCJIT. That's another story. But I'd like to compare us to QEMU. Okay, so we compare our throughput to QEMU using Spec 2006 integer because we're emulating an ARMv5 integer processor here, and the Embassy embedded benchmark suites. And I just want to make it clear here that we're measuring in instruction throughput measured in millions of instructions per second. The number of instructions, this is the number of target instructions executed. So this is the number of target instructions executed in the binary, not the host instructions, the target instructions. And this is the millions of those executed per second. So the dynamic instruction count is exactly the same between ArcSim and QEMU because we're running exactly the same binary, compiled exactly the same way, with exactly the same inputs. So there's no change here, so the instruction counts are the same, which means that throughput also directly correlates to the total runtime of the benchmark suite. So a higher throughput means a lower runtime, and that's the case here. Because we always beat QEMU, we constantly beat them. So the higher the bar here, the better, because that means we've got a higher throughput, which means we have a lower runtime, and we're continuously beating them. And a weighted harmonic mean here, it's weighted by instruction count, says that we're over 2 times better on average. And as you can see, in some cases, we are quite clearly better. So their Perl bench is running in QEMU at about 200 MIPS, I think, just a tad over 200 MIPS there. And then we're running at just under 800 MIPS for there. Sometimes we don't do as well, and that's the weird benchmark. So if anyone are familiar with the spec benchmark suite, we've got the likes of libquantum, which is really a pain, and it seems to behave really oddly. QEMU executes at just under 1,000. We operate at just over 1,000 MIPS there. So that's 1,000 million instructions per second. And we also evaluated us with Embassy as well, because Embassy is representative, I think, of embedded workloads here, and can really test the warm-up time of dynamic binary translators because they're so short running. We obviously don't want to introduce a warm-up penalty or any sort of unacceptable compiler delay here for such fast-running benchmarks. And in fact, we still beat QEMU across the board here. Again, with the same kind of variance, sometimes we're not as good, so I think conven 00 there, we're very, very close. Sometimes we're totally awesome. Like the fast Fourier transform in the middle there, we're performing at over 6,000 MIPS, and QEMU is just under 4,000. And on average, we're around about, I think, it looks to me just like less than 2 times on average is our harmonic mean here. So this goes to show that actually we don't suffer that much of a performance penalty. Given our short-running benchmarks here, so we even warm up pretty quickly as well. And yes, that's pretty much it for the alias analysis stuff. I'd just like to point to a few additional highlights of our instruction set simulator is that we support the partial evaluation that I mentioned before, so we do that so that we don't generate as much IR. We do region entry optimization so that inside a region we can actually perform optimizations across the basic blocks because we don't expose the block addresses for every basic block within the region. We chain regions together so that we spend as much time in native code as possible. So what we do is if we're jumping from one region to another region function, we just do a tail call straight into that region instead of going back to the interpreter, looking up the address and then doing a normal function call. We have our parallel compilation task farm, so usually we run as many compilation threads as we have cores -1, and then we use the final core to run the actual execution thread for doing single processor execution. We have really efficient interrupt handling code for doing user space interrupt handling and device interrupt handling. We have an instruction decode cast. We have a very extensive tracing and profiling infrastructure which we can turn on to give us metrics about the code that we're executing. And we also support multi-ISAs, so for the likes of ARM, we support ARM and we support Thumb, and we support switching between those in our instruction. So that's about it. I would welcome any questions that you have. Possibly, if anyone's interested, I may have some time to do some demonstrations across the road in the forum, but that's subject to you having a quick chat with me afterwards if you'd like to know any more about our simulator.
Have you investigated whether the existing type-based alias analysis metadata can represent your alias analysis information?
No, because sometimes I didn't think it applied as much. For example, obviously the type-based alias analysis works on types, but I thought that would be more representative of the types of elements that within a structure, whereas what we're doing is when we're accessing guest memory, we're just accessing an opaque pointer. It's just a pointer to anything, and the access could be 8 bits if it's an LDRB instruction, say, or it could be 32-bit access. We don't actually decorate that with the type information, so we haven't actually used type-based alias analysis here. Instead, we just propagate our own knowledge instead of trying to decorate it with the type-based alias analysis stuff at that time.
So the type-based alias analysis metadata is actually quite general, and I think it might be able to represent what you're looking at here. So it might be worth looking into.
Certainly, yeah. I mean, it's great to use the existing infrastructure there. Thank you.
So I'm pretty impressed that you managed to beat QMU on GCC and on the GCC spec benchmark. And I'm curious how many of your gains actually come from region formation versus better optimizations that LLVM provides, especially on GCC. I'd expect that you'd get a bunch of tail duplication, right? Whereas on the other benchmarks, you just managed to eliminate a bunch of code. And then how do you actually amortize the cost of compilation with LLVM, which is much, much bigger than what QMU has to do?
Okay, so to start with, the region formation part, it's static. It's 8K regions of code. Okay, that's all we do. We essentially, because we're emulating an application here, and we assume the 32-bit application, we assume a 4 gigabyte address space, and we just split that up into the pages, and then we create regions based on the pages that have been touched by code, so pages that we've executed. So that's static. There's no formation of different regions here. We just take those 8K regions of code, and that's all we do for that. There's nothing clever with the region formation there. Okay, so what was the other part of your question? What do you want to know?
Because usually when you region formation dynamically, you end up having to amortize the cost of region formation, especially like in GCC, you end up doing a bunch of tail duplication. But if you're not doing that, then you don't have to amortize that cost.
Well, exactly.
Right?
But yeah, because we don't do anything clever in that way, we simply just say, right, this is it. This is a region boundary. Maybe it's not great. Maybe sometimes we do have a little bit of jumping back and forth between regions. We've tried to be as good as we can by using this tail call mechanism for region chaining in order to reduce the time it takes, so we don't have to back out of the region, back to the interpreter, then go back into the function. We'll just try to get straight to it, just like that. And like I say, as the region becomes hotter, it'll get compiled again, and we'll get even better code and even better opportunities for optimization there.
So did you consider putting the virtual registers in machine registers some way?
I think that's probably handled by the optimization passes that LLVM does for us within our region. One of the optimizations that we do is for every, I mentioned that we create a basic block in the function for each target basic block that we've seen, but we don't necessarily take the address of every basic block, which means that LLVM's optimizations, such as the basic block merger and the optimizations that can work across the basic blocks within the function, can be really aggressive with the optimizations that they perform. So they really can promote memory into registers and keep things local. So for the example of a tight loop, we wouldn't have to write back into our CPU state structure at all within that loop until we actually came back out of the region. So that's something that's really heavily optimized by other aspects of our code, and the fact that we can keep things so local to a region, and we don't bother updating the CPU state structure until it becomes absolutely necessary. So until we do actually chain to another region, or until we back out to the interpreter.
Okay.
Did you consider adding support for the MMU?
We semi-support an MMU. We support an MPU-ish, but it's down to the way that the machine is described as well. So in our offline stage, it's it's an excellent way of describing. It's based on an ArchC variant, so we can actually describe a pretty good processor there. What I was actually talking about here was just the simulation of a user space binary. So MMU-wise, not particularly interesting, even though we do support M mapping within the user space stuff, and we do support memory protection as well. So if a user space program uses memory protection primitives like mprotect or mmap and applies protection to that, we do support that, and we do honor rights to memory that haven't been allocated properly as well. But as full system simulation goes, that's not actually what we were demonstrating here. So actually emulating an MMU in full was not really applicable in this case. Not that we couldn't do it if we built a full system model for what we were modeling. So.
Okay.
What is your slowdown factor compared to native performance?
Good question, thanks. I have recently done some tests on that, but I don't know off the top of my head what our slowdown compared to native is. I think if we were running these benchmarks on ARM and we ran in our simulator, we're not that slower compared to it than actually running it on Silicon. So I think maybe 2/3 were 2/3 slower, if I remember rightly. So no? 1/3 slower. So I was looking for my colleague for answers on that one. Thanks, Bjorn. 1/3 slower than native. In some cases, I mean, if you saw what I had on the embassy slide there, we're totally great on fast Fourier transform there. So there are certain workloads that respond really well to the optimizations that LLVM can perform on the code that we've discovered. So I mean, that's 6,000 million instructions per second there that we're running at for fast Fourier transform. It's incredible. I did double check that just in case I didn't make a mistake. But yeah, that was actually what was happening. Thank you.
So kind of back to his question, if you translate, say, from ARM to ARM, right? In an ideal world, you would never actually spill to your kind of virtual registers that you kind of that you simulate, right?
Exactly.
LLVM would figure out, okay, this is a one-to-one mapping between the registers. Yeah. So do you have a hunch for where you're missing information and where you're forced to do extra work just because of the binary translator?
In regards to what, ARM and thumb?
Just like in general, where so you suck in the ARM ISA and then you spit out more ARM ISA. What's the extra stuff that you're adding? What are the extra instructions that was not in native that are being executed in your translated executable?
Sorry, I don't quite understand. What are we doing in regards to what? Sorry.
What's the source of extra instructions that make your program 1/3 slower?
Oh, on native.
Yeah, if you compare native
right,
and
I see. So
self-translation, right?
Yeah, so see what the translator code we've got and what's on native. I guess that this is a guess because I haven't actually characterized it like that in full. We've had some issues getting some of our infrastructure to work on a 32-bit platform. Because we do this this contiguous memory stuff, we can be really efficient on a 64-bit host. We can directly access guest memory by using things like mapping an entire 4 gigabyte region and having the operating system do all of that for us. So when I tried to run this on a 32-bit ARM platform, we encountered some problems and introduced some slowdowns where we had to introduce a new page-based model. So that introduced further complications to the IRR that was generated, which kind of skewed the results that we'd be able to get to answer that question properly. So because we had to generate all of these different, these extra instructions around memory accesses in the guest memory space that we were emulating. So because we had to have extra stuff around these memory accesses, that also that was one source of problems in this case, but also it just sort of bloated the code somewhat, and it was a bit difficult to tell exactly on the stuff that wasn't to do with guest memory accesses. It kind of bloated it around that, and it was a bit difficult to tell. So I'm sorry, I don't have a definite answer for that, but we did have problems like porting our efficient contiguous memory system to a 32-bit host, which doesn't work in this case because it's 32-bit on 32-bit.
So I was just trying to find out, is there any way to get and play with this at all? Because it sounds really cool.
It is really cool. I'm very, very passionate about it. It's totally awesome. I love it. That's why I'm so excited about it. But no, is the answer. For a few reasons. If you are interested, I think I could get it going on my laptop. I'm not going to try here in case I embarrass myself. But if you want to see me afterwards, we'll give it a go and we'll see what we can do.
Cool.
Thanks.
I was wondering what version of ArchC were you using?
It's actually a heavily modified variant of ArchC.
Yeah.
So I don't know what the version number is per se, but we modify it quite significantly in order to support some of the clever things that we do in the JIT. We have to add intrinsics that allow us to describe which instructions are end of blocks. We also have the ability to switch the modes. So for the example, for the ARM and for switching between ARM and Thumbizer, we're able to decorate instructions with what might cause a mode switch and what the semantic instructions about how we actually do a mode switch is there. So I don't know what the version of ArchC is, but it is a heavily modified variant that we've customized.
Drawing from that, what version of LLVM?
I've been tracking head.
Oh, wow. Yeah, because the reason I'm asking is the last time I was using ArchC, it was limited to 2.9 or something. It was a pre-version 3 of LLVM.
Right, okay. So I mean, when I
the
say
mods you must have made must have brought it on a lot.
Well, when I say ArchC, that's just the language, the dialect. We don't use any tools for that.
Oh,
this is
okay,
our GenSim is the
yeah.
tool, so that's our tool. So that evolves with as we use it. So that evolves with us as we change the specification. We're not using anything else apart from GenSim here. GenSim parses the instruction behaviors in this C-like language and generates SSA forms for it. It parses the ArchC description and generates the IR metadata that's required for generating the interpreter and generating the instruction decoder and generating a disassembler and generating all the other parts that go to it.
So I suppose we have to buy GenSim as well.
Absolutely, yeah.
Maybe answering Chandler's question and also the recent one. Well, there is a way of getting hold of it. It's under a commercial license. We can certainly sort of work out the deal.
I'm glad my salesman's in the audience because I don't know how to answer that question.
So, time for one last question. Oh.
How do you deal with recompiling regions and the region chaining? Because presumably the region chaining is then pointed to the wrong place.
Yes, so we have, it's quite simple actually, we have a chaining table, and that's what one of the indirect things that you saw on the example was. So in fact this one, whoops, where is he? That one there, so that's one at the top is the jump location pointer. So this get element pointer here accesses the part of the CPU state that contains a pointer to a table that contains addresses of the region functions there. So that gets that, we get that back into the jump location pointer, and then we do an indirect tail call via that. So as a new region becomes available, we simply replace the entry in the region chaining table, just like that.
Thanks.
Thank you very much. Thank you.